Hi, everybody. So I hope everyone's doing well and staying healthy, keeping in high spirits. I know that this is a difficult time for everybody, and I just wanted to reach out and let you all know that I know this is hard. And I hope to regale you with some interesting stories today and get you thinking about the bigger picture about, we've talked about electrical fields, and we've talked about magnetic fields, and we're putting them together in terms of talking about electromagnetic waves, and we'll touch a bit also on an idea of quantum physics, which is talking about that light isn't just waves of electric or magnetic fields. Well, it is that, and it's also carried by something that's called a photon, which is a little packet of energy. So we'll talk about that today. And I'll also talk about something called Wiens Law, which talks about if something's hot, then it produces some radiation or some energy. So we'll talk about all those things. Today is going to be a combined lecture. So the topics are also going to stretch into chapter 26. You might know that our midterm number 3 will cover up through chapter 26, but today I'm going to guide you through some of the topics that I think are important for this. I don't know why it says X-rays. So X-rays. Okay, so today we're doing a combined lecture. So there will be no regular YouTube link posted for Monday. That will be that I would have done that around chapter 26, but I'm combining the two today. So this will be a little bit of a longer episode. In fact, one thing that I'll put in the description is I'll put the time at which I begin the discussion of chapter 26, so you can have sort of an idea of what to expect. So maybe before you start the chapter 26 lecture, maybe you take a few minutes to read through some of chapter 26 and just get a rough idea about what some of the topics are that we'll be talking about. This might help you to make some sense of things. For Monday, April 20th, we're moving on to chapter 28. That's going to be the lecture following our exam. So that's kind of looking not just next week, but the week after here. So that will actually be the next officially posted lecture will be for Monday, April 20th. I'll try to post it a day ahead of time or so. And that will be looking at some introduction to quantum physics, which I think is an interesting topic and something that we'll even touch on a little bit today in our discussion of the photon model of light. So these are the sections that I recommend reading before April 20th. So announcements. So this lecture, as I mentioned, covers Wednesday, April 8th, as well as Monday, April 13th. The office hours that I'll have are going to be from 5 to 6:15 on Monday. That's April 13th. And that'll be through Zoom. I will send out a link through Blackboard for that. And that will be your chance to ask any more questions that you might have. Also, I strongly encourage you to attend the virtual SI sessions. Those will be an excellent way to hone in on your skills and practice problems. You might notice that in the study guide, I've posted quite a few questions which are sort of intuition building ones. In other words, you might look at it. Oh, I have some nice decorations for today. So you might notice that there's this right-hand rule. It's very important, right? And so you need to be able to quickly determine which right-hand rule am I actually doing. And if there's my thumb, for example, is pointed in the direction of a current, then my fingers are pointed in the direction of the magnetic field. That's the first right-hand rule. The second right-hand rule has to do with this system of 3 here. And your book does it slightly differently, but the way that I like to do it here is that my finger is pointed in the direction of the charged particle motion, the velocity vector. My middle finger is pointed in the direction of the field, and my thumb will be, looks like I'm picking my nose, my thumb will be pointed in the direction of the force. So hopefully you can see that here, that in this particular case, that the force is actually pointed up this way, right? So practice that, make some sense of it, and remember that if you're using a negative charge, for example, an electron, that you're going to see a situation where the force is going to be exactly in the opposite direction. So as I mentioned, one thing you can do is use the right-hand rule and then reverse it, or the other way is you can use your left hand. So whatever works for you, as long as you're sure that you're getting the right answer each time. Okay, homework number 10, which is on chapter 25 stuff. This is due Monday, April 13th. And then finally, the homework from chapter 26 will be due on April 23rd. So that's a ways out. You might notice that you might be concerned maybe that, okay, well, wait, how is then the exam going to cover up through chapter 26? Well, for one thing, you will see that there's just going to be a few problems. So some small representation from chapter 26, so the majority from 23, 24, and 25. And maybe there will be a little bit more representation of those chapter 26 questions on the final exam. You can see the details of this exam on Blackboard, but just to summarize, there's 20 questions. They will all be in a multiple choice format. That's the best that I could do. I was going to do a numerical one. We might still do that for the final, but I think that I should give you some practice on how to do that, how to input answers so that it's not stressful for you. Homework number 10, as we mentioned, homework number 11, we mentioned the date on there. So I think I've covered all the announcements. Okay, very good. So moving along, we were talking about polarization last time, and the electric field for a light source, it kind of either oscillates up, down, or it goes left, right, or some combination of the two. So it could go from side to side, kind of in this 45 degree or 30 degrees or something like this. But when we go through a polarizer, it blocks out all the components that are going left, right, for example, in this situation. Sorry, this is kind of poor representation because technically it is like this, but the molecules are sort of aligned horizontally so as to block out the vertically oscillating things, and then just to let through the electric field in the horizontal direction. And so the way that we can do this mathematically is, well, so the description looks something like this here, is that we have an unpolarized light. That means that 50% of it is going to make it through any first polarizer. That means that half of the light basically happens to have components which is along the axis of the polarizer. So here are these little notches here on the side tell you the axis of that polarizer. And then if we send it through another polarizer, well, only part of those are actually going to make it through. And so, for example, in this case, the angle here is with respect to this vertical, which is the analyzer here. And so how do we figure out how much light is actually going to get through? So you can see here that for 0 degree situation, basically all the light gets through. For 45 degrees, it's kind of grayish, right? So you can see these kind of little blue and red lines behind here. They get kind of canceled out. And then if these polarizers are at 90 degrees with respect to each other, then they will completely cancel out. So there's a law for this called as Malice's law, and maybe I'll switch to the camera here to discuss this. So okay, so the way that I'll think about this here is that in this case, if the electric field is at some angle with respect to the vertical, we'll call that theta, as in the last picture. And so this is this after having gone through that polarizer that had this axis in this direction, with respect the same theta here. Then if it goes through another polarizer that's exactly at the vertical, right? So with respect to this here, then what we can do is we can say that the intensity that actually makes it through, so the transmitted intensity, is equal to whatever this I was here. So I'm going to call this I1 times the cosine of this angle, and we'll square it. So for example, if I have unpolarized light here, right, and we'll say this has some I naught, right, then I1 is actually going to be equal to 1/2 of I naught after it goes through this first polarizer. After it goes through the second polarizer, then we'll have 1/2 I naught times the cosine of this angle squared will be the actual transmitted light that gets through. So you'll see now that the light that comes through now has a vertical polarization, but the intensity has become less as a result of it. So that's the way that we think about these polarizers. So interestingly, light also becomes polarized if it reflects off of a surface. So for example, you might be skiing sometime, or maybe you're out on the water, and you see some light coming from far away that bounces off of a surface and then to your eyes. And it turns out that when it bounces, let's see if I can get my finger here. So if my finger is the direction of the polarization, then this one here tends to basically reflect with, okay, we won't say perfect reflection, but pretty good reflection. However, the vertical, when it actually comes down, it actually, what its meaning is the electric field is pointing up and pointing down. So when it actually hits the surface of some water or something like that, it's jiggling the electrons in the plane. And so one of the results of that is that that light is not reflected as well. So the tendency is that the light that comes, that reflects off is horizontally polarized. And so the way that you can calculate this is to say, well, whatever angle I have here with respect to the normal to that surface, and if I know the index of refraction, so for example of some glass, for example compared with air, I can figure out what that angle is that it makes 100% perfect reflection. This is called Brewster's angle. And I'm not going to emphasize this one as much. You should know how to use the formula, but we won't spend a ton of time on this topic. But I'll just briefly work out an example here. Is that so for Brewster's angle? If I have some surface here, and let's just imagine that this is glass, right, on this side here. And so that has an index of refraction of 1.5. And here is air with an index of refraction of 1.0, sorry. Here's N2, right? So our formula here is that the tangent of theta b is equal to N2 over N1. So in this case, if I wanted to figure out, hey, what's the best angle, right, such that when we have all of the different possible polarizations here, this is kind of just me drawing various polarizations that are coming in, let's say from something like the sun, and it's coming in at this angle with respect to the normal here, then what is the sort of ideal angle such that the light is completely horizontally, in other words, there's parallel to the surface here? Well, if we do tangent of theta b is equal to N2, which is 1.5, over 1.0, we can actually solve for 1.5 divided by 1, right? That's just 1.5. And if I do the arc tangent of 1.5, I'll get 56.3 degrees. So I have here 56.3 degrees as my theta b. So that means that this angle should be a little bit bigger than 45 degrees. And if that's the case, then I'm going to have almost exclusively horizontally polarized light. You may have an idea that this is useful if you were to be wearing polarized sunglasses. So for example, if you wear polarized sunglasses here and their axis is along the vertical, then all of the light that's reflected from this surface here is going to be blocked. And so you might say, well, wait a second, then that means that I can't see anything. But that's not true, because there's a lot of things. So for example, let's say there's a person over here, or let's say that, okay, this is not glass, but let's say that this is water, and there's a little fish down here. So here's Nemo. Oh man, that's a really bad picture of a fish, but I think you get the idea. You'll be able to see the fish, right? But, and you'll be able to see some corals and interesting things down there, but you won't see that light that's reflected off of the surface. Now, I'd like to demonstrate polarization for you as is reflected off of a surface. If you do happen to have polarizing sunglasses, one thing that I'd like for you to do is go outside and wear the polarizing sunglasses and try to look at the ground at this sort of angle here, the 56 degrees. It can be 45 degrees, it'll still work. And turn your head to the side and with the glasses on, or you can just turn the glasses at 90 degrees, and you should see it get darker or lighter. Now I'm going to try a little demonstration here instead, which is to be looking at a computer screen. Now it turns out that most computer screens, so here you can see, oh gosh, it's an upside down computer screen, but nonetheless. Here, I'll make it upright just so it doesn't look super strange. So here's the computer screen here. And here I have a polarizer. And so this polarizer here is meant for basically blocking out any light that is 90 degrees. You can see actually the little numbers here on this thing here. Is it in focus? Hopefully you can see that it has some numbers here, 0 at the top, 90 degrees over here where my mouse is. And so if I hold this up to the screen and I actually start rotating it, it actually becomes completely dark at this about, I'd say it's about 45 degrees or so. And then it becomes bright again. So here, that's interesting, is that I'm actually able to make it go from bright to dark to bright again. So that tells me actually something about the polarization, that it must be, it must be that the maximum polarization is actually at 45 degrees. And if I keep rotating this thing, it'll get dark again. So that's kind of interesting. As I rotate this thing, I'm actually able to completely darken, right? It's very, very dark. In fact, it's so dark that you're seeing the reflection of me back, right? And then there's the maximum there. And then now it gets light again, and you can actually see the things through there. So that's a polarizer. This is a really good polarizer, it turns out. And your sunglasses may be also pretty good. But nonetheless, I thought that this would be a good demonstration that would give you some idea of how polarizers are working, if in the case that you've maybe never used polarizing sunglasses before. Okay, so very good. So that is the concept of Brewster's angle. Light that bounces off a surface will actually have some polarization, and so then you can block some of it and reduce the glare. So this is just kind of a schematic here of that same picture here, is that the electric field, you're going to end up getting more of the horizontally polarized light compared with the vertically polarized light. And so just the vertical will pass through your sunglasses. Let's talk about another idea here, which is, why is the sky blue? So this is kind of an interesting topic for me. We often look out at the sunset, and as the sun is setting, we see the sky turn this brilliant color of red. So what's going on there? Is there some way that we can get a simple understanding of that? Well, it turns out that it's because of the particles in our atmosphere, and these are much, much smaller than the wavelength of light. So if you remember, the wavelength of visible light is somewhere between 400 nanometers up to 700 nanometers. So that's about half of a micrometer. So that's, on the order of 10 to the minus 6. And a particle is actually on the order of less than a nanometer. And so you think of, it's about like 100 times smaller. And so the gas molecules in our atmosphere, it turns out that they are less of an obstruction to long wavelengths than they are to shorter wavelengths. So blue wavelengths are shorter wavelengths, red wavelengths are longer wavelengths. And so this scattering, it decreases as 1 over wavelength to the 4th power. Well, so what does that mean? That means that if I have a really, really long wavelength, to say that it's really red, right, long wavelengths, then it's going to be a very small amount of scattering. And if it's a very, very blue wavelength, that's a very short wavelength here. If we do 1 over a small number to the 4th, we're going to see an increase in scattering. So blue light is scattered much more than red light. And so it's interesting that, so one of the ways that you can sort of picture this here is that if light comes from the sun, let's picture that the sun is coming from up above here at noon, then all of the red and blue and everything comes down to you, and the blue light is scattered more in the sky, which makes the sky look blue, and if you look all around you, you're going to see this bluish light. Now imagine that the Earth is now rotated, so it's 6 hours later, and the sun is setting. So if you're standing over here, you see this person standing to their side. They're looking up at the sun, but all the light that's come through, the blue light has scattered away more earlier, and so that's giving you this this effect that more red light is getting to your eyes. So that's kind of an interesting thing. That's called scattering. So let's take a look at some problems here. So, a radio antenna is broadcasting a 1 megahertz radio wave with 25 kilowatts of power. We're going to assume that the radiation is emitted uniformly in all directions, and we want to figure out the wave's intensity 30 kilometers away from the antenna. We want to figure out the electric field amplitude, and we want to write out the wave equation for this radio wave at this 30 kilometer distance from the antenna. So we're going to assume that it can be modeled as what your book is calling as a plane wave. So in order to solve the first part, we need to consider how do we think about power as it's spreading out from a source. So the first thing here that we'll look at, maybe I'll rearrange these slides here to this, that a light source that has a spherical wave, it spreads out from a point, then that means that it's spreading its energy out over more and more distance. And so if the power of the source emits uniformly in all directions, the wave intensity can be divided by 1 over r squared. So you can see here that this is 4 pi r squared. That's the area of a sphere. And so so you can imagine that it's the same amount of power distributed around the sphere. So here's kind of my simple picture of it. Looks something like this. That I have some kind of source of light, right, that's going out in all directions, right? And so we have some power that's radiating outward. And if we draw an imaginary circle around this thing here, we can say, well, all this power is being distributed in a certain amount of area, right? And so if this is an area here of radius r, right, then the area of this circle here is 4 pi r squared. So in other words, the intensity is going to be equal to the power divided by the area, which in this case is going to be 4 pi r squared. So in other words, if r gets bigger, right, then we have more area, and so the intensity is actually going down. So in the case for our problem at hand here, if we had our intensity is going, or sorry, our power is going to be 25 kilowatts. That's 25,000 watts. Seems like a lot, right? And we want to figure out what is the wave's intensity at a distance of 30 kilometers away, so 30,000 meters away. So in order to do this here, we can apply this equation here. We can say that 25,000, or 25 times 10 to the third watts, divided by 4 pi times 30 times 10 to the 3 squared, right? And this will be now meters squared. So we're going to have a unit of watts per meter squared as our intensity. So in other words, intensity has the units of watts per meter squared. So it's an amount of power, so I'll say the units here is watts per meter squared. So let's go ahead and just calculate that here. So I'll just bring up my calculator, and this is 25e3 divided by 4 times pi times 30e3 squared. And so we have our answer here then is going to be 2.2 microwatts per meter squared. Doesn't sound like a lot, but it turns out that that's actually enough to pick up a signal and be able to hear something like a radio broadcast. Let me also just refresh our memory here about how does this whole game with frequency and wavelength play a role. So remember that we can say that the speed is equal to the wavelength multiplied by the frequency, right? And so in other words, the speed in this case of this wave is equal to the speed of light, c, which is 3 times 10 to the 8th meters per second. And that's going to be true for all different forms of light, whether it's a radio wave, whether it's a microwave, whether it's X-rays, or whether it's visible light that we can actually see. So this is, so all EM waves, all electromagnetic waves will travel at this speed. The frequency here was given as 1 megahertz. That's 1 times 10 to the 6 hertz. So therefore, we can actually solve for lambda, which is going to be c divided by f. So 3 times 10 to the 8th divided by 1 times 10 to the 6th. This is meters per second. this is going to be hertz, or in other words, 1 over seconds. So when I put in these numbers here, you can see that this is 3 times 10 to the 8th divided by 1 times 10 to the 6th. And our number here is 300, and so our units, 1 over seconds cancels out, and our lambda is equal to 300 meters. So this is our wavelength in this case. And yeah, so this is a wavelength of light for 1 megahertz light, 1 megahertz. And that'll come into play in just a moment, but I figured I'd just cover that while it seemed relevant. So the next thing we have to do is figure out what the electric field amplitude is at this distance. Well, in order to figure out the amplitude of the electric field, we should think about the definition of how electric field is related to intensity. So in other words, intensity is equal to, and you can either write it with regards to the electric field or with regards to the magnetic field. And as we've learned so far, the electric field and the magnetic field are both propagate. I actually like this type of visualization here. This is just showing an electromagnetic wave which is propagating, and you can see that the wavelength here is from one peak to the next peak, and you can see that the magnetic field is going sort of in the XY plane, whereas the Y is this axis over here, whereas the electric field is going up and down in the ZY plane. And so this is the sort of a visualization for how an electric field propagates. If you remember from last time, we were talking about the electric field and the magnetic field, that they are both propagating together. So if we wanted to figure out what the electric field is, well, we can just relate that to our result before from the intensity. So the intensity we found from last time was 2.2 microwatts per square meter. So if I put that in here, I can say 2.2 times 10 to the minus 6 watts per square meter. And if I rearrange all these things here, so in other words, I multiplied by 2 divided by epsilon naught times c, and it looks like if I take the square root of all that, then I'll get then I'll get E naught, right? So I just rearranged this equation here to get E naught. So I brought the 2 up, I brought the c and the epsilon naught down, and I took the square root. So if I plug in all these things here, I'll get 2 times that 2.2 times 10 to the minus 6, and divided by epsilon naught, well, we're going to have to look up what is that epsilon naught actually. That epsilon naught is 8.85 times 10 to the minus 12 in SI units, and then finally the speed of light, which is 3 times 10 to the 8th. So in other words, when we plug all these numbers in, so in other words, we'll do the square root of 2 times 2.2 times 10 to the minus 6. Let me also minimize this one here so you can see the equation that I have at the same time I'm typing it in. Divided by 8.85 times 10 to the minus 12 times 3 times 10 to the 8th. And if I plug all this in, I get 0.041. 0.041. What are my units? Well, if you remember that the electric field is either in volts per meters or newtons per coulomb, right? So those are two kind of equivalent ways of writing your electric field. So my electric field is equal to this. Okay, finally, now we're going to bring into our play here that last part, which is write out the equation for this radio wave at 30 kilometers distance from the antenna. We're going to assume that at that place that it can be modeled as a plane wave at that distance. So what we can say then is that the electric field is given by this equation here, where we need to actually have the period, which is 1 over the frequency, and the wavelength, which we actually computed as 300 meters. Let's go back to thinking about how do we actually get the period from the wavelength. Well, if you remember from our discussion around sound waves, the period is 1 over the frequency. So in other words, if the frequency is equal to 1 megahertz, that's 1 times 10 to the 6, then period is 1 over 1 times 10 to the 6, and this is units of hertz. Remember, hertz is 1 over seconds, and so we have 10 to the minus 6 seconds, or in other words, 10 to the minus 6 seconds, just to write it out carefully. That's going to be my t in this case. And the wavelength, we figured out what the wavelength was a moment ago, was 300 meters. So putting it all together now, just bring this guy up here. We can see that E is equal to E naught. Let me just copy it all down carefully here. Times the sine of 2 pi x over lambda minus t over capital T. And so now I can just plug in the things that I need. So in other words, lambda is 300 meters, t is 10 to the minus 6, and E naught we found was 0.041. So 0.041, that's finally going to be in volts per meters. And then sine of 2 pi times x over 300 meters minus t over 10 to the minus 6 seconds. And so that is going to be my equation for the propagating light. Now let's actually just check something here. I'm kind of curious, like, if this represents sort of a sine wave, and that sine wave is moving, then what if I were to pick a place where this is 0, right? So the 0 happens when sine of all, whatever is inside of here, if that's equal to 0, or if it's equal to 2 pi or something like that, then that's going to be sort of a 0 position. And so as this wave is moving, let's see if we can move along with it. Well, that would be the situation where the whole argument of this thing always remains 0. So in other words, if x over 300 is equal to t over 10 to the minus 6, then we'll be traveling with this wave all the time. So notice how we can rearrange here that x over t, that's like a speed. And if that's equal to 300 divided by 10 to the minus 6, that's going to equal to, sorry, I'm running out of space here. That's going to equal to 300 times 10 to the 6, or 3 times 10 to the 8th meters per second. So in other words, that's the speed of light. So in other words, we can get the speed of light simply by taking the wavelength and either dividing by the period or multiplying by the frequency, which is the same thing that we found up here, that velocity is equal to wavelength times frequency. So that's just kind of an encoding of that in this crazy looking little equation here. You can also write the magnetic field in the same way. It's just that we'd have to use this part of the equation here to solve for B naught, and we'd put that in over here. Okay, very good. Let's talk about a new situation here, which is to talk about the photon model of light. And so one of the types of questions that you might see is, what is the energy in eV of a photon of visible light that has a wavelength of 500 nanometers? Well, so in order to do this, we need to figure out a way to relate energy to wavelength. Well, fortunately, your book has a very simple equation that relates how the energy of a photon is actually related to frequency. And so maybe we can use that with our knowledge of how frequency and wavelength are related in order to figure out how wavelength is related to energy. So I'm just going to write down that equation here, that E photon is equal to h times f. And this h is a constant, and we'll talk about that in a second. This is called Planck's constant. And we also saw that c is equal to lambda times f. Those are going to be the two equations that we sort of need here. And so if I were to straighten out my camera here, so this h here is called Planck's constant. And it turns out that it is a constant that relates the frequency of light to the energy that the photon has. It's not an obvious thing at all, but it turns out that that's the relationship between frequency and energy. So the higher the frequency, that means the more blue that the light is, or maybe if it's more X-rays or something like that, then it's going to have a higher energy of photon. And so in this case, we were actually given a wavelength, and we were being asked what the energy is. Well, in order to do this, we need to actually figure out, well, how do we relate this in terms of if frequency is equal to c over lambda, we can put this in over here. And so I can say that E of a photon is equal to h times c divided by lambda. So this is an equivalent way of looking at this problem. Well, I guess we need to know what h is. So if I go to the Wikipedia site for Planck's constant, you can see here that the value of h is given in something called joule seconds. So I'll write that one down, and I'll go back to that in a second. So 6.626 times 10 to the minus 34 joules times seconds, or 4.13 6 times 10 to the minus 15 eV times seconds. So this is my H here. We're going to use the one that's in eV since we were asked in this case what the electron volts was. So here, if we do 4.136 times 10 to the minus 15 eV times seconds, and we have C, well, we know what C is. That's 3 times 10 to the 8th meters per second. So interestingly, it looks like our seconds are canceling out here. And then we're dividing by the wavelength, which was given as 500 nanometers, sorry. So 500 times 10 to the minus 9 meters. So the meters here are canceling out, and now we're only left with eV. So if we plug in those numbers into a calculator here, we'll plug in Planck's constant, 4.136 times 10 to the minus 15 times 3 times 10 to the 8th, and then divided by 500 nanometers. When we do that, we'll get 2.48. And the units is in this case is going to be eV. So this will be equal to 2.48 electron volts. So the energy of a photon is apparently 2.48 electron volts in the problem that was being asked here. So electromagnetic waves, even though they are waves, they have these particle-like properties, and these particles are called photons. And interestingly, the energy of a photon is just directly related to the photon's frequency. So we found that a 500 nanometer wavelength for a photon has an energy of 2.4 electron volts. So how do we actually make electromagnetic waves? Well, one thing that we can do is we can use an antenna, and what that basically does is it drives charges back and forth, back and forth. And so it turns out that charges, when they're accelerating, actually produce electromagnetic waves. And so that turns out to be the primary way to actually create electromagnetic waves, is to actually oscillate some charges back and forth or accelerate them. And that will actually cause the charges to emit electromagnetic radiation. So how do then electromagnetic waves interact with matter? Well, if you think about it, we talked about an electrical dipole moment, right? So for example, this is a water molecule here with the 2 hydrogens and an oxygen. And if the electric field points up, it's going to try and orient itself to that field. And then suddenly, if the electric field tries to point down, it'll try to orient itself in a different way. So in other words, if we got the electric field oscillation frequency just right, we could get this molecule to shake, or in other words, to rotate back and forth. And it turns out that this is exactly how a microwave oven works. So when you put your oatmeal in the microwave and you press go, there's actually, I'll cut to the camera here just so you can see me. In the side of your microwave is basically an antenna, which is causing a bunch of charges to oscillate up, down, up, down, up, down, and that's producing microwaves. Now the reason it's in a metal box is the metal box is actually keeping those waves from getting out to you. But if those waves hit any water, and also other things, unfortunately, like some plastics or some ceramics, those will also heat up. And so you might notice for certain types of bowls that you put in the microwave, maybe not glass, but maybe certain glasses, that you'll notice that the outer side of the bowl gets very, very hot. What's supposed to happen is that the water molecules themselves are supposed to start jiggling really fast, which is creating heat. And that's the primary way that a microwave is actually working. Now let's talk about, so we're just doing sort of a drive-through here of some of these topics. So unfortunately, none of you had the chance to actually do this lab here, but in the lab, you basically take different filaments, and you are basically trying to figure out the thermal emission spectrum of a glowing filament. And then based on that, you can actually figure out what its temperature is. And so there's a very simple way of relating the peak wavelength that is emitted by something to its temperature. So you probably have heard this expression, red hot, right? Well, it turns out that the hotter that something is, it actually shifts more to the blue. So here's something that is at 3500 Kelvin, but as you go up to 4500 Kelvin or 5500 Kelvin, the peak wavelength actually shifts to the blue. So in other words, to shorter wavelengths. This is called Wiens Law, and the way to calculate this peak wavelength here is to take this number, 2.9 times 10 to the 6 nanometers times Kelvin, and simply divide by the temperature in Kelvin. Let's actually practice for a couple of these scenarios here. So, for example, if I had 3500, temperature is equal to 3500 Kelvin, then I can use this formula here, 2.9, let me make sure I write it down correctly, times 10 to the minus 6 nanometers times Kelvin. And if I divide by 3500 Kelvin, (2.9) times 10 to the minus 6 divided by 3500 Kelvin, I will get I'm sorry, it's not 10 to the minus 6, 10 to the 6. Okay, sorry, I just realized I made a mistake. 10 to the 6. Then we'll get 828.5 nanometers. Let's go ahead and check that out with what the slide was saying. So sure enough, for 3500 Kelvin, 829 nanometers, or I calculated 828.5, was the peak of this emission. So that's in the infrared, which is a little bit beyond what our eyes can see, but the tail of this is in the visible, so you should be able to at least see something if there's a filament that's 3500 Kelvin. Now let's go a little bit hotter. Let's go up to 4500 Kelvin. So we're going to just basically take the same formula here. Notice that the Kelvin and the Kelvin cancels out, and we're left with nanometers. But now I'm going to take the wavelength peak is 2.9 times 10 to the 6 nanometers Kelvin, and we want to divide by 4500 Kelvin. Well, in that case, I'll just take my calculator, and I'll just change this to 4500 Kelvin. So in that case, I get 644.4 nanometers. And finally, in the case of 5500, which is pretty close to the temperature of the surface of the sun, that wavelength of peak, and I'll just say for 5000 Kelvin, is equal to 527.3 nanometers. So let's go ahead and take a look then and see if the slides are agreeing with our calculations. So at 4500 Kelvin, sure enough, 644 nanometers, so this is shifting more into the yellow. And then at 5500 Kelvin, which is close to the surface temperature of the sun, the peak wavelength is around 527 nanometers, which is kind of green light, actually, which might make you wonder if the peak of the light that is of the wavelength of light that's coming from the sun is green. You might wonder, why are all the plants green? Because if they're green, that means that they're reflecting green light, and they're not using the most abundant color that is being produced. It's kind of interesting, huh? So, in other words, as a filament gets hotter and hotter and hotter, instead of it becoming so-called red hot, it actually becomes blue hot, or whiter hot, if you want to think of it like that, because white means that the spectrum is going to basically be very broad, and so if you add all the colors together, you're going to get what looks like a whitish light. Okay. So, could you determine the temperature of a filament if you found, let's say you measured the spectrum of the light bulb and you found that its peak wavelength was 1200 nanometers? Well, let's go ahead and take a look at that. So, if we took let's say that in the lab you actually used something called a spectrometer and you measured a peak, right? So this is going to be your peak wavelength, going to be somewhere over here like this. And that peak wavelength that you measured was equal to 1200 nanometers. And so what if you were asked, hey, can you make a guess based on that? So this would be like the intensity, right, that you measure with your spectrometer device. Could you make a guess what the temperature is? Well, you could, because you could rearrange that equation that we just did before, which is 2.9 times 10 to the 6 nanometers Kelvin. and we could instead just divide by the wavelength in nanometers. And so in other words, cancel out the nanometers, and we'll say we have 2.9 times 10 to the 6 divided by 1200, and that temperature should ultimately be in Kelvin. Let's go ahead and calculate that. So 2.9 times 10 to the 6 divided by 1200 is 2400, well, 2416 if you want, or 2417 Kelvin is my estimated temperature of the filament. Now this might sound ridiculously hot, right? I mean, most regular ovens only go up to about 500 degrees Fahrenheit, which is something like 200 or 300 degrees Celsius. And so how could it be that we're getting up to the thousands of Kelvin? Like, why doesn't it just melt everything down around us? Well, the answer is because this filament here is actually very, very tiny. So it's not producing a ton of heat energy, but it is actually at this very, very high temperature. And in fact, it's not unusual for filaments to be the same temperature as the sun, because if they are that same temperature, then they're actually producing a light that is very similar in its basically in its spectrum compared with the sun, which might look kind of natural to us. It also looks a little bit extra bright. If you have a filament that's at the same temperature as the sun, say 5,000 or 5,500 Kelvin, it does look like a whitish light, but a lot of people say that it feels a little bit too bright or too sort of harsh in terms of producing bluish light. And so most people prefer for their indoor lighting at night to have a bit more of a so-called warmer color, which is to say that if you're using an incandescent light, this means a lower temperature filament. Okay, so that's how temperature of something that's hot is it's also called as a black body in your book. As it heats up, this tells you what wavelength it actually emits. One other interesting application is that we are about 300 Kelvin. And so if you take a look at this here, if we do 300 Kelvin, you can see that about 10,000 nanometers, which is the same thing as 10 micrometers, is the wavelength that we emit just based on being warm. And so this is used in a lot of military applications for so-called night vision goggles, that if anything is warm, then it emits light that's at 10 micrometers wavelength, which is way outside of our normal vision. But if you have a special kind of goggles that you can see at these wavelengths, then you'll be able to actually see that. Okay, let's talk about frequency and a wavelength here. And let's also combine into the mix a review of the photon energy. So I'll give you a moment to try and think through this here. I'll give you a moment to read the question, and in a moment we'll come back and look at it together. Okay, so my hope is that you took a moment to reflect on the equations that we've gone over so far and tried to figure out which ones are relevant, and applied these to figure out which you think is the correct answer. So if you had chosen D, you were correct. Let's take a look at how to solve a problem like that. So we have two different cell phone, we have two different phone frequencies. One has a frequency of 850 megahertz, that's 10 to the 6 hertz. And the other one, F2 we'll call it, the digital phone, has a frequency of 1.9 gigahertz, or in other words, 1,950 times 10 to the 6 hertz. And we're being asked, the digital signal, the F2, does it have a shorter wavelength or a longer wavelength? Well, in this case, I can think through it like the following. I can say, well, you know, it seems to me that this is the one with the higher frequency. And so I know that wavelength is equal to C divided by F. So in other words, if the frequency is higher in this case, then the wavelength must be shorter. So this one has the shorter wavelength compared with F1. And the second thing that we're asked to think through is, what about the photon energy? Well, in order to do that, we might take a look at thinking about the second equation that we had, which was energy of a photon And I'll try to write EPH to remind you that this is the energy of a photon, not the electric field, right? And this is equal to H times F. So in other words, you can see very clearly here that the one with the larger F is going to have the one with the larger field, larger photon energy. So this is also going to have a higher photon energy. So shorter wavelength, higher photon energy in this case. Okay, very good. Let's take a look at the next question here. What if we had two radio signals and they were both being emitted at the same power? So let's say both are at 50 watts, but the AM signal has a frequency of 850 kilohertz and the FM signal has a frequency of 85 megahertz, right? So at a much higher frequency. Which signal has more photons per second? Okay, so if you had guessed A in this case, that the AM signal has more photons per second, you were indeed correct. Let's take a look at how to solve a problem like this. So the photon, we're going to use the same ideas as before, that E is equal to H times F, or that E photon is equal to HC divided by lambda, right? There's another way of looking at it here. And but in this case, since it was given as in hertz, we can actually just use E is equal to HF. And but we'll also think that power, right, is equal to energy per time. So this means that, well, the energy is going to be equal to HF for each photon, right? Times the number of photons, right? So this is going to be the number of photons here, divided by the amount of time is going to be the power. So in other words, if we wanted to figure out if we were given the power, right, as 50 watts, and we wanted to figure out the number of photons per second, right, then we should solve for this part here, and that the number per time, right, or number per second, is equal to the power divided by the photon energy. So power divided by HF. So in other words, we can see here readily that if both of them have 50 watts, and we have H and we have F, the one with the larger F is going to have the smaller number of photons per second. So in other words, the lower the frequency that you have, right, then the larger this number of photons per second is going to be. We can compute these things if we just simply use H in the units of SI units. So in this case, I'd like to use the joule unit. So in fact, we're going to calculate then for, let's say that if F is equal to, let me just make sure I have the numbers correct here, 850 kilohertz. So 850 times 10 to the 3 hertz. Then let's calculate the number of photons per time. So if we did this here, we can see that this is the power is going to be 50 watts, that's joules per second. And I'm going to use my H here is now 6.626 times 10 to the minus 34. That's going to be joules times seconds. And then finally, the frequency here is going to be 850 times 10 to the third 1 over seconds. So the 1 over seconds and seconds cancels out, joules cancels with joules, and we're going to just be left with 1 over seconds. Well, that just means the number of photons per second. If we put these all together in a calculator, let me bring this over here so you can see everything at the same time. 50 divided by 6.626 times 10 to the minus 34 times 850 times 10 to the third. And you'll actually see, wow, that's a lot of photons per second, which is 8.9 times 10 to the 28th photons per second. So one thing I'd like to challenge you to do is to repeat the same calculation, except instead of 850 kilohertz, I'd like you to try putting in the 85 megahertz. If you think about your favorite radio station, maybe that's 91.1 or 107.9 or 101.3, right? Those are all numbers that are in megahertz. And so those are the numbers of an FM radio station or frequency modulation radio station. And so you can think that what's happening is that they're sending a large number of photons per second your way, and you're capturing those with an antenna. It's a pretty wild story, but that's the basic physics behind how radio waves are working. So in other words, one of the takeaways is that the frequency that had the smaller frequency ended up having more photons per second. Maybe one way of also thinking about that is that because it has less energy per photon, we need to send more of those photons per second in order to make up make up for the fact that each photon doesn't have as much energy as, for example, as compared with an 85 megahertz wave. Okay, so this concludes the discussion around Chapter 25 topics. And maybe if you want to take a breath, then we'll move on now to the some basic discussion topics of Chapter 26. Okay, so this is a somewhat abbreviated discussion of Chapter 26, and I think that the idea here is just to get a very basic overview of how AC electricity works. So first off, what does AC mean? Well, it means an alternating current. And so let me turn to the camera here, and I'll give you my just very simple perspective here, is that we saw before in a wire that the current was going through the wire just one direction. Well, now it's like the current is going one way and then the other way and then this way and then back, right? And we actually see some motivation for that, which is our discussion about a generator, is that if we had a magnet and we had some wire that was spinning around, part of it is going to make the current go one way and part of it's going to make the current go the other way. So in other words, a generator is a good way to actually produce this so-called AC current. If you want some entertainment, you can look up videos about Nikola Tesla versus Thomas Edison. They were competing for whether or not the United States would be on AC electricity or DC electricity. And so it wasn't an obvious choice at the time. And now it's an even less obvious choice because we actually have now a lot of transformers which work on DC. And so there's now a reignited discussion on, well, what should we do actually? You know, should we maybe think about switching to DC now? Is that a better idea? So none of these answers are obvious, but I just wanted to mention that. I think it's kind of an interesting idea. So AC means alternating current, and we're going to talk about how do we actually quantify it if it's moving. Basically, the electrons are going one way and then the other way and then one way and then the other way. So there's an alternating that's actually happening. We're also going to talk about transformers and figure out what are they good for. How do we actually make calculations to figure out how they can make the voltage become higher or lower. And then we'll conclude with a little bit of electrical safety. So first I'll mention here that this is what the EMF, or in other words, the voltage source, looks like for an AC voltage source. And so you notice that there's some familiar language here, right? The period is equal to 1 over the frequency, just like we had covered a moment ago. And the you can see that it's either a trough to a trough or it's a peak to a peak, but in other words, the time that it takes for a signal to repeat itself is the period, so one oscillation period. And so in the United States, this period, the frequency is equal to 60 hertz. And so I'll just quickly just do a calculation here, which is that in the United States, we use frequency is equal to 60 hertz. That means that the period, right, in other words, the time between oscillations is 1 over 60, that's inverse seconds, and just using a calculator over here, that is equal to 1 over 60, which is 0.017. So in other words, that's 17 milliseconds is the amount of time that it takes. So in other words, the oscillation that's happening here, 17 milliseconds is the amount of time that it takes, roughly. Maybe, you know, if we go to more decimals, is 0.0166666, but okay, 0.017 seconds, or in other words, 17 milliseconds, is the amount of time that it takes for this oscillation to repeat itself. So also from here to here is also 17 milliseconds. So that's the meaning of the period of this electrical oscillation. So we'll often see in the in the textbook they use this shorthand omega, and where omega is the angular frequency. And basically the reason for doing that is maybe it's simpler than it seems here, is that if you wanted to express this wave here, you could say that the EMF is as a function of time is equal to E naught times the sine of something, right, times t over capital T, the period, right? And you could say, well, I want it so that, I know that the sine, every time the sine gets up to 2 pi, then I've repeated myself, right? So every time that this has gone around one full cycle here, then it's repeated itself. So basically I want to say that when little t is equal to capital T, that would be 1. But if I then put in a 2 pi in there, then that means that by the time that t gets to capital T, then this is 1, and we'll get to a 2 pi. And if t gets to 2 times capital T, then that'll be 2 pi, and I'll go through 2 cycles, and so on. So you'll see that this is the kind of way that we write things. And if we kind of combine all this together, you can see that, well, that's E naught, or what is that, EMF naught times the sine of 2 pi f t. So this shows up enough. So remember that frequency is equal to 1 over the period, right? That's how I was able to rewrite that. And so 2 pi ft, the 2 pi f here is often written as omega. So this is sometimes written then as the E naught times sine of omega t. It's just a little bit more of an elegant way of writing things, just so you don't have to write every single time 2 pi t over capital T or 2 pi f times t. Sometimes we just write that omega there. So that's the reason for that. So that's the kind of oscillation. And so generally, our simplest model here is that we might have a resistor that is connected, connecting a circuit through to an AC source. And so it turns out that Ohm's law is valid for resistors when an AC voltage source is used. And so in other words, either the current is going to go this way or the current is going to go this way, but we'll find that Ohm's law, in other words, delta V is equal to the current times the resistance, is always going to be true in this case. In other words, we take any moment in the cycle here and we figure out, well, what is I and what is V, even though those are both changing in time. If we take the division between those two, we'll be able to figure out what the resistance is. So, for example, here is a picture that shows the voltage drop across the resistor as it's oscillating through time, and also the current through a resistor also as it's oscillating through time. And one thing I want you to notice is that they're both oscillating together. In other words, when the voltage goes up, the current goes up. When the voltage goes down, current goes down, right? So they're related to each other by some multiplication. So as we mentioned, that electric outlets in the US wiggle up and down 60 times per second, or in other words, every 17 milliseconds. So let's take a look at a specific example here. What would be the value of the resistance in this case? Well, if we want to look at this here, we can see, I see that we have 10 volts, and then this purple line here is showing 0.50 amps. So in other words, I could find some other place along here as well, like so minus 10 and minus 0.5, or any place along here, but maybe a convenient place is just to think about the very beginning or the very end here. If we divided those two, in other words, if voltage, delta V, is equal to 10 volts, and the current is equal to 0.5 amps at some moment, then we should be able to figure out the resistance then, that the resistance is equal to delta V divided by I. So if that's true, we can write 10 volts divided by 0.5 amps. And that is actually telling us then that the resistance then is equal to 10 divided by 0.5 is equal to 20 ohms in this case. So the resistance is equal to 20 ohms for this situation here. Let's take a look at the second question, which is, what is the frequency of the voltage or the current? This is, I guess, is a little bit of a strangely worded, not the voltage divided by the current. I'll just say the voltage or the current. Because they have the same frequency. And what is the Average power dissipated, well, we'll look at that second, so, or after that. So what is the frequency? Well, we can see here that the total time for this waveform to repeat itself is 0.04 seconds. So we don't even need to write something down. We can actually just directly calculate that we know that the frequency is equal to 1 over the period. So 1 over the period, then that means that we have 25 hertz is our frequency. So in other words, just to be clear, what I did here is I recognized that the period was 0.04 seconds. That's the same thing as 40 milliseconds. And then I used that frequency is equal to 1 over period, so I did 1 over 0.04. So converting between period and frequency is something that we've practiced before, and I do want to, you to practice that and make sure that that's a skill that you've got down. So that's 25, is that 25? 25 hertz is the frequency of this signal. Okay, now lastly, we're asked, what is the average power dissipated in the resistor? Well, this might not be the most obvious thing because we can't exactly use our previous ideas around current and power. We have to think about this a little bit differently here. So if you think about the sine wave looking like this, if we actually took the power, it's going to be the square of this, which actually looks like this. And so if we took the average, we'd get 1/2 I squared R. And so that turns out that the power that's dissipated is going to be 1/2 I squared R is going to be our actual power that's dissipated over a cycle. So in other words, here, if that IR, remember that was a peak, so we're going to do 0.5, that's 1/2, times our IR, which we saw was 0.5, and we're going to square that. And then we're going to multiply by the resistor value. Well, we figured out that the resistor value is 20. So that tells us that 2.5 watts is the amount of power dissipated in this resistor. So again, what I did is I said power is equal to 1/2 IR squared multiplied by R. And we figured out what R was earlier. That was 20 ohms. And IR, the peak current, was 0.5 amps. And we plugged all those things in, and we got that 2.5 watts is what is actually being dissipated in our resistor. So this brings us to another topic here, which is there's this concept called the root mean square for both the current and the voltage. And the RMS, or the root mean squared, is defined like this. You just take the peak value and you divide by the square root of 2, and then you'll get this so-called RMS value. Now, why is this useful? Well, it's because basically we can write that the power that's dissipated in a resistor is just I squared R, which you've seen before, but instead of I being the peak current, it's this so-called RMS value. So basically what we're doing here is, do you notice how, like, if you just had this current here and you say, well, okay, well, what's the average current? It's like kind of a nonsensical question, right? Because it's going to be 0. But if we square it and then we take the average of that, right? And then we took the square root of that, then this is the so-called root mean squared of this quantity. Okay, so that's the meaning of this so-called root mean squared. And it turns out that if you took the RMS value of the current and the RMS value of the voltage, if you multiply those two together, then you'll actually get the power. So in other words, this is very similar then to the expressions that we got before for using DC currents, except the only difference is that we have to make sure to use this RMS value. So that's a little bit of a tricky part here. Okay, so we went through those questions here. What is the name of a device that's used to change the voltage of AC electricity? Give you a moment here, press pause and think through it. Which one do you think it is? If you had guessed transformer, then you were correct. No, this is not transformer robots in disguise. But it is a technique that's used to either step up or step down the voltage that's being produced. And you'll see in a moment why this is actually useful. So a transformer, if you have a voltage connected to one side, imagine that that has a coil that's going around an iron core. Like, so for example, see this square here. And what you're actually doing is you're inducing a magnetic field, which as it's changing back and forth according to Faraday's law, that means that we're actually inducing a current in the secondary coil. And it turns out this can be done with remarkable efficiency. And so this is some technology that was even available back in the days of Thomas Edison and Nikola Tesla. So there was an argument that said, well, why don't we just use these transformers to, at the source of generation, to step up the voltage to extremely high voltages. And then once it's gotten actually to the people who are going to use it, then we'll step it back down. And you'll see in a moment why we would actually want to do this. So it turns out that I'm not going to derive this here. Your book has the derivation of it. That if you wanted to figure out the voltage that is measured across this coil, it has to do with the number of turns of the secondary coil compared with the number of turns of the primary coil. So for example, let me just give some very basic example here. If we started off with, let's say, 100 volts, and so we'll say V1 is equal to 100 volts, and the number of turns of the first one was equal to 10 turns, and the number of turns of the second one was equal to 200 turns, then we might be trying to figure out, well, hey, what is the voltage of the secondary? So we can actually use that V2 is equal to N2 over N1 times V1, and so in this just example problem here that I'm saying these are some of the givens here, we can say that V2 is going to be equal to 200 over 10 times 100. And so if we multiply all those together here, let's see, this 1 0 cancels out, so it's 10 times 200, so that's going to be 2,000 volts will be V2. So in other words, by having more turns on the second side compared with the first side, we'll be able to get a larger voltage. This will be times V1. So, oh, I'm sorry, volts, which is actually 20 times V1, right? So you can see that the ratio here is just the ratio of N2 to N1. Okay, so why would long-distance power lines be at a high voltage then if the standard US power outlet has an RMS voltage of only 120 volts? And actually, you know what, I'm going to pause for a moment to just start to demonstrate something to you. I have brought a little demo, which is going to be to bring a voltmeter, which I think all of you have had some experience with when we were doing the labs. Okay, so I'll do my best here to do this one-handed here. I have a power strip, which is connected into the wall. And I have a voltmeter, which I think that most of you have had some experience working with at this point. And so I have these two leads here. Notice that they have plastic around the outsides because I'm going to do something that might look like it'll be a little bit dangerous, right? So I'm going to turn this voltage meter here. Now I'm wondering if I can actually, this might be too tough to do here. Yeah, cool. Okay, good. So you can see the voltmeter here. And I'm going to hold this here, and I'm going to stick one of these guys into the socket here, right? And on the other side, just kidding, sorry. I'm okay. I'm just sticking plastic in I'm holding onto the plastic side. Now, if I touch the metal side, maybe I'm in trouble, okay? But I'm okay. Everything's fine. We're looking here, and you're seeing that this is given as the AC voltage. Well, it's not giving you the average voltage. That's 0. What is instead being reported is the RMS voltage. So that is what is being reported by this ohm meter, is a 116.6. We can just round that and say that it's 120. In fact, if my refrigerator clicks on right now, well, it doesn't, but if it does, then you'll actually see this number fluctuate. So it fluctuates just a little bit, but it's usually somewhere around 120 volts. So, okay, so that's kind of our demonstration for how AC works. And now I'm going to go back to this slide here, which says, so 120 volts is my RMS voltage. I just kind of demonstrated that to you by using a voltmeter. Okay, so then why would they go through all this trouble from the generation plant to step it up to 10 kilovolts and then to 500 kilovolts and then step it down, and then step it down to your house lines. That's those little boxes that you see sometimes out in the streets. Maybe you've seen those. Those are the step down transformers, right? And so that involves basically this technology where you have coils of wire wrapped around an iron core. Why would they go about doing all this? Well, by stepping up the voltage at the power plant so that these transmission lines could be very many miles or hundreds of miles long, and then operating those at high voltage and then stepping them down just outside of your front door, it turns out that the overall efficiency of this multi-step process is actually much better than just sending you the 120 volts across all those ways. Let's work out an example together that helps to make some sense of that. So we're talking about transmission lines carrying electrical energy at some specific rate. So for example, let's say that we're sending 120 kilowatts from a solar farm to a town that's 10 kilometers away. So imagine that we're going to somehow convert this solar farm into AC. So I won't mention about how that's done at the moment, but just you can just imagine that. So actually solar is producing DC electrical energy. But let's just calculate the efficiency if we're going to send this down a transmission line that's 0.4 ohms. So I'm going to write down some of my facts here. The power is equal to 120 kilowatts. And the distance over this distance here, this distance is equal to 10 kilometers. But more importantly, that the resistance of this line over the full 10 kilometers is 0.4 ohms. So we're going to try to figure out how much power is actually dissipated in the wires. So here's the generator. Here's like the smokestacks or something like that. And it is producing some electricity that's going finally to your house. So this is just a symbol of your house here. Maybe put some windows in there and the front lawn or something like that. Okay, good enough. I think you get the idea. And then finally, then this has to kind of return, right? And so what we're saying is that the total resistance of this whole circuit here, right? So if we were to model this as a circuit, it would look something like this: a resistor, and then it goes back, right? That's a very boring picture of this whole thing. And what we're getting here is that the resistance of this whole wire, the whole way through, that the resistance is equal to 0.4 ohms. So how do we figure out then the amount of power that's dissipated in this resistor here? Well, one thing that we can do is we can take a look at the voltage, right, which is equal to 240 volts, and this is an RMS value, and we can see that the current then RMS that's going through this wire here must be equal to the VRMS divided by R. So in other words, that's 240 volts divided by 0.4 ohms. So putting all those facts together, we can see that 240 volts divided by 0.4 is going to be 600 amps. Wow, that's a lot of amps. And so one thing that we can use then is, based on our previous analysis, is that the power that's dissipated is going to be equal to I squared RMS times R. So if we plug those numbers in, 600 squared times 0.4, so we'll do 600 squared times 0.4. Wow. We see that there is a lot of power that's dissipated in this resistor here. So now let's take a look at a different situation, which is actually using a step-up transformer, which has 20 turns on the primary coil. N1 is equal to 20 turns, and then on the secondary side, N2 is equal to 2,000 turns. Now let's take a look at this particular case here. So what we're talking about here in this case is that we're going to say that V2 is equal to N2 over N1 times V1. And so In other words, uh, instead of the solar farm producing the normal 240 volts, if we have 2,000 and versus 20, then 2,000 over 20 is the same thing as, what is that, 200 over 2 or 100 over 1. So that's 100 times 240, which is going to be equal to 240 kilovolts. So 240 kilovolts is our voltage. Now, if we think about, okay, the IRMS is going to be equal to this VRMS, which is 200 and, just give me a second here. So at this higher voltage here, if we are to be transmitting the same amount of power, remember that the power introduced in the problem was 120 kilowatts, then the IRMS in this case is going to be power divided by this new voltage here. And so, so remember P is equal to V times I. So here we have 120 kilowatts divided by 240 kilovolts. And so if we look at the division of those two numbers here, we'll see that it's 120 times 10 to the third divided by 240 times 10 to the third. And now we actually have a current of only 0.5 amps. That's a lot lower than the 600 amps. And so correspondingly, we can see that the 0.5 squared times 0.4, 0.5 squared times the 0.4, so similar like we did in this earlier calculation here, that this is going to be the power dissipated in the wires, all right, power dis, right, is only equal to 0.1 watts. So in other words, the thing that I want to drive home is that there's a very, very small amount of power that is actually dissipated in the wires themselves when we do this step up. And so then what would actually happen in practice then is that we would have then, well, I guess they have a picture of that in the slides, but I'll just show this, my picture here is that this is the power plant. They're producing, so this is a transformer sort of picture here. So this is many, many turns here, right? It goes across and then goes to some box that then does another transformer to step down to your house, right? So here's your house, right? So that's the basic picture here of how it works. And so that's my really crappy cartoon picture, but the nicer picture is actually this one here. So the power plant steps up, transmits perhaps a very long distance, and then there's actually usually two stages of stepping down, sort of a local substation, and then the step-down transformer that happens at the street. Now, the one that's on the street, maybe you've seen these pictures, or maybe seen pictures, you've seen this in real life, these little boxes up here. If you haven't seen them, maybe go walk around your neighborhood and see if you can notice this thing. And inside, if you were to open it up, you'd actually see that there's an iron core inside and that there's two posts here that then send some wires around one side and then around the other side. And what ends up happening is that the transformer then converts this distribution voltage to be 120 volts RMS, which is basically what you saw today when I measured the voltage in my own home. So how does it work actually with these power outlets here? Well, this one side goes to one end of this sort of like, if these are the two eyeballs and this is the mouth, I don't know, of these, the way that our circuits look, you're essentially plugging through to between these two some load. So for example, a hair dryer or a rice cooker or something like that. We usually call the high voltage side as the so-called hot side, and then there's another side which is called the neutral side, which is normally connected to ground. That's the larger one. And actually, one little interesting fact is that it's the larger one is the one that's the neutral one that's connected to ground. And maybe part of the reason why you can how you can remember this is that the smaller one is too small for a kid to stick their finger into there. And so they would not get shocked if they actually managed somehow to get their finger into the larger one. So the smaller one is the so-called hot side. Just kind of a little mnemonic to remember it. So what about different devices? So what if we had a bunch of different devices that were plugged into the same circuit breaker in the house? So this circuit is protected to be able to supply up to 15 amps. But let's say that we have our stereo going and a lamp and a heater and a computer all plugged in. So the question is, does the circuit actually blow? I'll give you a moment to see if you can think through that. So looking at this kind of problem here, we can actually see that all of these devices will just add. So in other words, if we were to add 250, and I'll just add it here in this calculator. It's a little easier than writing it and then calculating it. So 250 to 900 to 100 to 120. We can see that the total amount of power here that's consumed, P total, is equal to 1,370 watts. So if our voltage that we normally use, our RMS voltage, is equal to 120 volts, we can use P is equal to VI, where of course just V and I now are RMS values, to solve for I, which is going to be P divided by V. If we do that here, we can see that P, which is 1370 watts, divided by 120 volts, that is going to give us 1370 divided by 120, which is going to be 11.4 amps. So the IRMS is going to be 11.4 amps. So I would say you're safe. You're not going to blow the circuit just yet. But if you plug in one more thing, maybe a coffee maker, maybe a hairdryer, then we might go over the limit and we might blow the circuit breaker, which means that we've gone too high of current. And the purpose of a circuit breaker is to prevent the wires from heating up too much so that they don't cause a fire in your house. So it might feel inconvenient at some times that if you blow a circuit breaker, but it's actually it's a protective measure. So how much would it cost if you leave all these things running for 2 hours? Well, it turns out that the cost of electricity is 16 cents per kilowatt hour. And so one of the calculations that we can do here is that we can say, if you wanted to figure out the total amount of energy, remember that that's just going to be equal to power times time. And so in other words, if you had 1370 watts times 2 hours, then that's going to, we can multiply those two numbers together. Oops. 1370 times 2, and we'll get 2740 watts times hours, which also sometimes people write as 2.74 kilowatt hours. And so ultimately that's what you pay for is kilowatt hours. And if we multiply this by $0.16 per kWh, then we can actually see 2.74 times 0.16. We can actually see that the cost for doing this is going to be $0.438. So basically almost 50 cents to run all those things for 2 hours. So that's kind of an interesting sort of cost analysis. Last thing I want to talk about is physiological effects and electrical safety. So basically, this little chart here tells us that if you have a milliamp of current running through us for AC, that you maybe feel it. And if you have 15 milliamps, you might actually cause paralysis of the respiratory muscles. And if you're greater than 100 milliamps, or that's 0.1 amps, then that might be enough to actually be fatal. And for DC, that's going to be more than 500 milliamps. So in fact, this reason right here was one of the arguments that Edison had for why we should use DC, is because you have to have a much higher threshold of DC current in order for it to be fatal. So if that's the case, let's take a look at these two scenarios. In this case, we have a worker who is touching some pole which happens to be connected to 240 volts. Do you think that this person is safe or not? And then what about in this situation where they grab onto something, maybe by accident, to something where it's 240 volts, but they are holding their other hand onto a railing which is grounded? Well, you might think that it would be dangerous in either case, but it turns out that the worker's rubber shoes protect him from a shock in this case. And so if you look at all the different resistors, maybe the resistance of the skin, the body, and then the shoes and the floor, you can see that there's a very large amount of resistance connecting him to ground, Whereas in this second scenario, there's not the rubber shoes anymore because the current is going to go directly through from one arm to the other and through the heart, which is the most serious problem with this picture here. And so this could cause the cardiac arrest. So if you look at these resistances here, this is only 1.5 kiloohms for 240 volts. And so we can say that current is equal to voltage, 240, divided by resistance, which is 1500. And you can see here now that we have 0.16 amps. Well, that's 160 milliamps, and that's definitely more than the fatal effect for heart fibrillation. So that's a very serious situation here, 160 milliamps, compared with this situation where we only see 240 microamps. Okay, so finally, I will just conclude with a few review questions that I think will be helpful for you as you're preparing for the midterm. So I might ask you to take a few moments to see if you can work these ones out and press pause, and then when you come back, then I will show you how I work out these questions. Okay, so for the first question, we're asking which would drain a battery faster, a circuit with a resistance of 10 kiloohms or a circuit with a resistance of 1 ohm. So in light of the fact that we're not quite given numbers here, maybe we could actually come up with some numbers on our own. So for example, if we had 10 volts here on both of these situations, what we're really looking for is the amount of power that's dissipated in this resistor. So if it's a DC circuit, we can simply say that it's equal either to the V squared divided by R in this case, right? Or we can do I squared times R, but in order to get I, we would have to figure out what the I is for both of those situations first. So this might be the more direct way of figuring out the rate at which energy is spent for the battery. So if we had 10 volts squared divided by 10 kiloohms, and I'll also work that out over here, power over here is 10 volts also divided by 1 ohm. So you can see very readily that this is 100 watts dissipated in the 1 ohm resistor. But for the 10 kiloohm resistor, we can see that this is 10 squared divided by 10 to the third. So in this case here, we have 0.01 watts is actually being dissipated in the larger resistor. So in other words, the larger resistor has a much, much lower power, and so therefore it's going to drain the battery at a very, very slow rate compared with the 1 ohm resistor. In fact, there's many circuits that are just meant to do one thing. For example, a little light that flashes maybe once every minute or two for your fire alarm. You notice that you don't really have to change the battery for your fire alarm very often. It may be because this is consuming an extremely small amount of energy to make that light flash every now and then. And so that actually might mean that your fire detector can last for years without you having to change the battery. Let's take a look at the second question here. Let's draw a circuit with a battery connected to 4 resistors. So we have R1, R2, R3, and R4. And R1 and R2 are connected in parallel, and R3 and R4 are connected in series. So let's see what it looks like here to draw that. We'll have a battery here, and then we'll have R1 and R2, which are connected in parallel, and then we'll have R3 and R4 are connected, oh, sorry, I made a mistake. R1 and R2 are connected in parallel, and R3 and R4 are connected in parallel, and both parallel pairs of resistors are connected in series. So let's take a look here. So certainly this is correct, but let me draw it in a slightly different way. So if we had R1 and R2 are in parallel, here's R1 and R2, and R3 and R4 are in parallel, but then this group and this group are now in series with each other. Let me see if I can give you the full picture here. Okay, so that's how we could draw. It was one way to draw all these things together. Another possible way that you might consider having drawn this is something that looks like this. This is also correct. So there's a number of ways that you could go about drawing it, but that is a situation where R1 and R2 are in parallel with each other, and R3 and R4 are also in parallel with each other, but this group and this group are in series with each other. Okay, very good. Lastly, we're being shown a circuit here in which resistor R2 is adjustable. So as its resistance is made larger, we're wondering what will happen to the voltage at point A compared with the negative terminal of the battery. So in other words, we're trying to figure out how does it change as we change the how does the voltage drop across R3 change as we change the resistance of R2. Well, this is actually a voltage divider problem in disguise here, because the R1 is not going to change. There's going to be 20 volts across that R1 no matter what. So for our purposes, just for looking at this situation, we can sort of ignore that for the moment, because that's not the thing that's changing here. That there's going to be 20 volts on this side, and there's going to be 0 volts on this side. And so if this resistor here becomes larger, then according to the voltage divider, well, so one thing you could do is you could say, well, I'm going to have, this is R2 and this is R3. And you could say, well, I'm going to have a current which is going to, so here's what we'll do here. So maybe you can appreciate that whether this is resistor here across here or not, there's still going to be 20 volts on this side and 0 volts on this side. And so one of the things that I know is that if I take the voltage drop across this R2 here, it's going to be equal to the current times the resistance 2. If I try to measure the voltage drop across R3, that's delta V3, this is going to be the current, same current, times the resistance through through R3. If I combine these two resistors here to figure out what the total resistance is, I can figure out that the total current, right, that's going through this part here, well, I'll call this the current that's going through resistors 2 and 3, this is going to be equal to 20 volts divided by R2 plus R3. So therefore, I can plug this in here, that delta V2 is equal to 20 volts times R2 over R2 plus R3. And similarly, V3, delta V3, is equal to 20 volts times R3 over R2 plus R3. So maybe now it's becoming more clear that if we make R2 bigger, then we're making this part on the bottom bigger. And so we're making overall V3 to go down. Whereas if we're making R2 bigger, you might be thinking, well, wait a second, the amount of current is becoming less, so what's going on here? But also there's this term on the top here too. So there has to be 20 volts that drops from here, going across here to going across here. And it turns out that the larger R2 is, then the more voltage is going to be dropped across the larger resistor. And this is the principle of the voltage divider. So, so the meaning here is that as R2 gets bigger, more voltage drop will be across R2, and less of the voltage drop will be across R3, as is shown by this equation here. Thank you for watching. I hope this was useful, and that concludes our discussion of Chapter 26. There will be no lecture posted for um, the 13th. This was that lecture. And the midterm will be on April 15th. Please see the Blackboard announcements for that, for the details on that. Thanks, and please take care and have a good day.